It's 1687, and Isaac Newton has just published his magnum opus, Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. What is now known as Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and direction, unless acted upon by an unbalanced force. In other words, inertia. And this was revolutionary. But what if you were a scientist before Newton? Or more accurately, what if you were born after Newton but didn't know about this book? Well, then you'd be kind of screwed, because the world would never be the same again. So let's talk about why you wouldn't want to be an early light theorist. The Age of Enlightenment began in the late 17th century and continued through the 18th century, marking a transition period from the Middle Ages to modern times. This was a philosophical movement that emphasized reason, individualism, and skepticism towards traditional authority, and it's for this reason that we have movies like Monty Python and the Holy Grail, where King Arthur's knights go around killing people and destroying property while quoting logic and reason at them. It was also during this time that great scientific discoveries and inventions were made and theories were proposed by the likes of Newton, Galileo, Descartes, Boyle, and many others. But unfortunately, those who proposed certain ideas were sometimes persecuted for their beliefs. Take Galileo Galilei, for instance. He was an Italian astronomer who lived from 1564 to 1642. Which puts him smack dab in the middle of this era. He was one of the first astronomers to use a telescope, and he made several important discoveries about the moon, planets, and stars. However, when he published his theory of heliocentrism, which is the idea that the Earth and other planets revolve around the sun, he was put on trial by the Roman Inquisition. See? That challenged the long-held belief that the Earth was the center of the universe, a belief that was supported by the Catholic Church. He was found guilty of heresy and sentenced to house arrest for the rest of his life. Isaac Newton was also alive during this time, living from 1643 to 1727. He made groundbreaking discoveries in mathematics, physics, and astronomy, including the laws of motion and universal gravitation. However, he didn't publish his work until after the death of his contemporary, Robert Hooke. You see, back in the day, scientists didn't have the benefit of peer-reviewed journals to share their findings. Instead, they would often present their work to professional organizations or fellow scholars directly. Sometimes they'd even publish their work anonymously or under a pseudonym. Now, we don't know exactly why Newton did this, but it was probably because the scientific community was very competitive and cutthroat. They had something called priority disputes, where scientists would argue over who was the first to come up with a certain idea or discovery. There was no official system for acknowledging and crediting scientists for their work, so they often felt the need to publish quickly and anonymously to get their work out there before anyone else could claim it for themselves. And if that wasn't enough incentive, science was generally looked down upon by society as being some kind of applied philosophy rather than a legitimate field of study. So scientists often had to hide their identities to avoid ridicule or persecution. Now, all of this brings us to Robert Hooke, an English natural philosopher and architect, who lived from 1635 to 1703. During his lifetime, he was a prolific writer and published many scientific papers on a variety of topics, including mechanics, optics, and astronomy. He made significant contributions to our understanding of elasticity and made the first compound microscope. But most importantly to our story, he was one of the first scientists to propose a theory of gravity. Now, Hooke didn't develop a complete theory of gravity like Newton, but he did propose the idea that the Earth and other planets are attracted to the Sun by a force that varies inversely with the square of the distance between them. He also believed that this force was responsible for keeping the planets in their orbits around the Sun. However, he never published his theory of gravity. Perhaps because he was too busy working on other projects, or maybe because he feared ridicule or persecution. And here's where things get really interesting. You see, when Newton published his own theory of gravity in the second edition of Philosophiae Naturalis Principia Mathematica in 1666, he didn't mention Hooke at all. Instead, he gave most of the credit to himself, saying that he had derived his law independently. Now, this led to a bitter argument between Newton and Hooke, with each man accusing the other of stealing their ideas. However, most historians agree that Newton's theory was indeed original, and that he was the first to develop a complete and coherent theory of gravity. So was Hooke really the first to propose a theory of gravity, and did Newton steal it from him? Well, not exactly. The answer is yes and no. Hooke was certainly one of the first to propose a theory of gravity, but he never published it, so it didn't really exist outside of his mind. Newton, on the other hand, did publish a theory of gravity, but he didn't give Hooke any credit for his earlier work. So, yeah, Newton did kind of steal from Hooke, but not in the way that you might think. So what does this mean for the hypothetical person who was alive during this time and wants to make a name for themselves in the scientific community? Well, it means that you would have to be incredibly careful about what you share and when you share it. If you're working on something big, you might want to hold off on publishing it until you can get some recognition for it. You also need to be prepared for a lot of competition and skepticism. People will doubt your ideas and try to tear them down, and if you're not careful, they could take your ideas and claim them as their own. To succeed as a scientist during this time, you would need to be extremely dedicated, persistent, and thick-skinned. But it wasn't just the cutthroat competition that made this a difficult time to be a scientist. The lack of support from society also played a major role. During the early days of science, there was little understanding or appreciation for what scientists did. Many people saw science as nothing more than a branch of philosophy or a hobby for rich amateurs. This lack of respect made it hard for scientists to make a living and often forced them to take on multiple jobs or to rely on wealthy patrons for funding. This meant that many scientists had to work in secret, hiding their identities to avoid ridicule or persecution. For example, one of the earliest scientists to study electricity was a British natural philosopher named William Gilbert. He published a book on the subject in 1600, but he used the pseudonym Patient Mendes to avoid being identified as the author. This was because electricity was seen as a strange and even dangerous phenomenon, and Gilbert feared that his reputation would be ruined if people knew he was studying it. Even famous scientists like Galileo and Newton had to deal with the lack of support for their work. Galileo was forced to recant his heliocentric theory, and Newton was often criticized for his unorthodox ideas. Despite these challenges, scientists during this time period were able to make some incredible discoveries and laid the foundation for modern science. People like Robert Boyle, who was one of the first to study the properties of gases, and John Ray, who made significant contributions to the study of light and optics. These scientists, along with many others, helped to pave the way for future generations of scientists, and their work continues to inspire and amaze us today. Imagine you're a physicist living in the late 19th century. Ah, that must have been an exciting time to be alive. The Industrial Revolution was in full swing, and new technologies were emerging left and right. You're interested in the newly discovered phenomenon of radioactivity, but there's a problem. You're a woman. At this time, women were not allowed to attend university, let alone become professors. So, how do you break into the field of physics and make a name for yourself? Well, you could try to find a wealthy patron who would fund your research. Or maybe you could try to sneak into a university and attend classes in secret. Or maybe you could just give up and accept that you'll never be able to make a contribution to physics. But wait, there's another option. You could move to France, where women were allowed to attend university and become the first female professor of physics. Marie Curie did just that, and her research on radioactivity led to the development of X-rays and nuclear energy. Without her pioneering work, who knows where physics would be today? Let's imagine that we have time traveled to the early 1800s, and we are trying to convince people that light is made of particles. We have brought with us all of the evidence that physicists have gathered over the past 2 centuries. Diffraction, interference, the photoelectric effect, Compton's scattering, pair production in high-energy physics, superconductivity, quantum optics, quantum computing. We have the mathematics of wave mechanics and quantum field theory. We can even show them images of the very first stars that humans ever detected beyond our solar system. Indirect evidence of exoplanets by the wobble they cause in their parent stars. Gravitational microlensing images from the Webb telescope. We can tell them about the cosmic microwave background radiation and the 2.7 Kelvin temperature of space. We could even show them images of distant galaxies moving away from us, and use that to calculate the rate of expansion of the universe and estimate a value for dark energy. We know that the speed of light in vacuum is exactly 299,792,458 meters per second, and we can demonstrate that this speed is constant to a few parts in 10 to the 15th power. And if that weren't enough, we can also show them images of black holes and gravitational waves. So, let me ask you, would you want to be a physicist at this time? I think not. Because despite all of the evidence that we have brought with us from the future, we will not be able to convince anyone that light is made of particles. At best, we might be able to persuade some open-minded individuals that maybe light is made of both waves and particles. But the vast majority of people will reject our ideas out of hand, because no matter how much evidence we present, there will always be some small number of physicists at that time who will claim that all of these observations can be explained by a simple reinterpretation of Maxwell's equations. They will say that these physicists simply don't understand the true nature of the electromagnetic field, and that those who do understand it, the true believers in the wave theory of light, will see that everything we call the particle nature of light is just an illusion caused by our own ignorance. This small cabal of heretics will be led by one man, a man whose name has become synonymous with the wave theory of light, a man whom you may have heard of, James Clerk Maxwell. You may be surprised to hear that Maxwell was not actually the first person to propose the idea that light is an electromagnetic wave. That honor goes to the French physicist Augustin Jean Fresnel, who proposed it in 1816. However, Maxwell took the idea and ran with it. deriving what are now known as Maxwell's equations from a set of three fundamental principles, which he published in a paper in 1865. In that paper, he showed that these equations could be used to predict the behavior of electromagnetic waves in various situations. But Maxwell never actually derived these equations from first principles. Instead, he simply assumed that the same laws that govern the behavior of magnets and electric circuits also govern the behavior of light. And then he showed that if you assume that light is a wave, then these equations can explain all of the properties of light that were known at the time, including the conservation of charge, the behavior of electric circuits, the properties of magnets, and even the behavior of the newly discovered phenomenon called radio waves. Maxwell had shown that all of these phenomena could be explained by assuming that light is a wave, and he did it without any experimental evidence whatsoever. He based his entire argument on a set of assumptions that he said were as self-evident as the law of gravity. And it wasn't until years after his death that people realized that the assumptions Maxwell had made were not actually self-evident at all. For example, one of Maxwell's assumptions was that the speed of electromagnetic waves in a medium is equal to the product of the square root of the permittivity times the permittivity of that medium. When Maxwell wrote this equation, he didn't know that it was actually an identity. It was only after he died that physicists figured out that this expression is actually just the definition of what we now call the speed of light in that medium. So really, Maxwell had simply assumed that the speed of light in a vacuum is equal to the speed of light in a vacuum. But at the time, no one knew that this was even a thing that could be possibly tested. But while Maxwell's ideas were elegant and simple, they were also extremely controversial. In fact, when Maxwell first presented his ideas, they were rejected by pretty much everyone, including the editors of the journals where he tried to publish them. And this was because Maxwell's ideas went against the prevailing view at the time, which was that light was made of particles. The particle theory of light had been around since the time of Newton, and it was supported by a lot of experimental evidence. For example, light could be scattered by particles in the atmosphere, causing the sky to be blue. Light could also be polarized by passing it through a material that had its own electric polarization, and this could be used to measure the distance to nearby stars. There was also the Michelson-Morley experiment, which had recently failed to detect the luminiferous ether, the supposed medium that light waves were thought to propagate through. All of this evidence seemed to point to the conclusion that light was made of particles. Despite this, Maxwell's ideas eventually won out, and the wave theory of light became the dominant paradigm in physics. There are a number of reasons for this. One was that Maxwell's ideas were more elegant and simple than the competing theories. Maxwell's equations were a beautiful set of mathematical relationships that captured the essence of the relationship between electricity and magnetism. This made them very appealing to many physicists, even if they didn't necessarily agree with all of Maxwell's conclusions. Another reason was that Maxwell's ideas were more consistent with the known facts about light than the competing theories. Maxwell's theory was able to explain all of the known properties of light in a simple and elegant way, whereas the other theories were more ad hoc and difficult to work with. Finally, there was the issue of who was making the arguments. Maxwell was one of the most brilliant physicists of his generation, and his ideas carried a lot of weight. His collaborators and colleagues were some of the most respected scientists in the world, and they were very effective at promoting Maxwell's ideas. On the other hand, the main proponents of the competing theories were relatively unknown, and their ideas were considered to be controversial. Nevertheless, the shift from the particle theory of light to the wave theory of light was not an easy one. It was a long and contentious process that took several decades. Even after Maxwell's death, his ideas were still hotly debated. It wasn't until the late 1800s, when physicists began to develop new and better ways to measure the properties of light, that the wave theory of light finally began to win out. By the early 1900s, it had become the dominant paradigm in physics, and it has remained so ever since. So, if you find yourself in the early 1800s trying to convince people that light is made of particles, you have an almost impossible task ahead of you. Even if you bring all of the evidence that physicists have gathered over the past 2 centuries, it's unlikely that you'll be able to change anyone's mind. The particle theory of light simply had too much momentum at the time, and it would take decades of further evidence and theoretical development before the idea that light is made of particles would finally catch on. Now, let's dive into the tale of Thomas Young and the double-slit experiment. Who was Thomas Young? Thomas Young was an English polymath who is often remembered as one of the founders of modern linguistics. He published many works in various fields, including an English grammar book that remains popular today. But did you know he also played a key role in advancing our understanding of waves? He was the first person to demonstrate the wave nature of light, which is something that even Einstein had a hard time accepting. In fact, Young's experiments are what led him to formulate his famous thought experiment known as the double-slit test. So let's take a look at who he was and why he matters for the science of sleep. Thomas Young was born in 1773 in Conshire, England. His father was a farmer, and Young had 4 brothers and 3 sisters. However, his family wasn't poor, and they were able to send Thomas to the best schools in London to receive an elite education. When Thomas was only 14 years old, he was already fluent in Greek, Latin, and Hebrew, and he was well versed in mathematics, natural philosophy, which is an old-fashioned term for physics, and chemistry. He graduated from Cambridge University in 1791 and began studying medicine at Edinburgh Medical School. Soon enough, he was considered the most brilliant member of his college, and after graduation, he returned to Cambridge to become a fellow and tutor. Around this time, he published his first paper on the subject of light and color. He realized that when white light passes through a narrow slit, it doesn't form a bright spot in the middle of the screen behind it, but rather it forms a pattern of alternating dark and light bands, now known as an interference pattern. He then repeated this experiment with different colored lights and found that the pattern produced by yellow light differed from the pattern produced by blue light. From this, he concluded that color isn't a property of objects, but a property of light. This was a pretty radical idea, because up until this point, scientists believed that colors were produced when objects reflected certain kinds of light waves. But Young proposed that different colors of light have different wavelengths, and that these wavelengths interfere with each other to create the colors we see. This discovery earned him a place in the French Institute and the Royal Society. He spent the next decade building on his theory of light, all while working a full-time job as a physician. He looked at how light reflects off of different surfaces, and how it refracts, which is the bending of light as it passes from one transparent substance to another, such as from air to water. He discovered that when light passes through a prism, red light bends at a different angle than blue light, meaning that white light can be separated into its different colors. These ideas were very controversial, however, because they challenged Isaac Newton's corpuscular theory of light. According to Newton, light is made up of tiny particles emitted from objects, and the different colors of light are caused by differences in the mass of these particles. Young didn't believe this, because if light was made up of particles, then when two beams of light of different colors overlapped, they should simply add together to create a brighter light. But Young's experiments showed that instead they interfered with each other, creating areas of high intensity and areas of low intensity. To explain these findings, Young proposed that light behaves like a wave. While this idea was more or less accepted within the scientific community, there was still one thing that puzzled Young, and that was the photoelectric effect. In 1801, Young observed that when light shines onto certain metals, electrons are emitted from the surface of the metal. This observation didn't fit well with his wave theory of light. If light was a wave, then increasing the brightness should increase the energy of the emitted electrons. But in reality, the energy of the emitted electrons depends on the frequency of the light, not the brightness. This observation would later play a key role in Einstein's development of his special theory of relativity. You see, the energy of a wave depends on both its frequency and amplitude. Frequency refers to the number of waves at a second, and amplitude refers to the height of the wave. So if you were to increase the frequency of a wave while keeping the amplitude constant, the energy would increase. Likewise, if you increased the amplitude of a wave while keeping the frequency constant, the energy would increase. Now, in most cases, increasing the brightness of light is equivalent to increasing the amplitude, but it's not necessarily so. For example, radio waves are a form of light, and the brightness of radio waves is measured in milliwatts per square meter. Meanwhile, the energy of visible light is measured in watts per square meter. So increasing the brightness of radio waves wouldn't necessarily increase the energy. To increase the energy of radio waves, you'd need to increase their frequency. The same goes for visible light. Increasing the brightness doesn't necessarily increase the energy, and this is why Einstein's discovery was so revolutionary. He figured out that the energy of light isn't just a property of its frequency and amplitude, but is also a property of its wavelength. In other words, the energy of light comes in discrete packets that behave like particles. These packets are now known as photons. The energy of a photon is proportional to the frequency of the light and inversely proportional to its wavelength. This means that to emit an electron from a metal surface, a photon must have a minimum frequency and a minimum energy. If the frequency of the light is below this threshold, then no electrons will be emitted regardless of the intensity of the light. But enough about Einstein. Let's go back to Thomas Young. After wrestling with the photoelectric effect for a few years, Young gave up on solving the problem and turned his attention back to optics. He wanted to figure out how the eye perceives color, and while reading an article about the anatomy of the eye, he had a sudden realization. What if the eye has 3 types of receptors, one for red, one for green, and one for blue? And what if all colors we see are combinations of these 3 colors? To test this hypothesis, he decided to do what is now known as the Young-Helmholtz trichromatic theory. This experiment required a special device called a kaleidoscope, which consists of a tube with mirrors set at either end and colored glass or beads placed inside. As light passes through the tube, it's scattered by the beads, creating a pattern of colored dots. Young used this device to project a small dot of light onto the retina of a monkey. The monkey was able to tell the animal that the dot of light was red, green, or blue, depending on which receptor was being stimulated. From this, Young concluded that all colors can be explained by three primary colors: red, green, and blue. We'll talk more about the physiology behind color vision in a future video. But for now, I just want to say that Young's ideas really advanced our understanding of how we see color. So far, I've mostly been talking about Young's scientific discoveries, but one of his most important contributions to science was actually a thought experiment. In 1801, Young wrote an essay called A Letter on the Nature of Light and Images. In this essay, he describes an experiment that illustrates the concept of interference. His experiment consisted of shining a beam of light through two slits onto a screen. If light travels like a wave, then when it passes through two narrow slits, it should create two separate beams of light on the screen behind it. However, instead of seeing two spots, Young saw a pattern of alternating bright and dark bands. He was able to explain this pattern by assuming that light interferes with itself, meaning that at any given point on the screen, the resulting intensity of light is equal to the sum of the intensities of the individual waves. In other words, the peaks of two waves overlap, resulting in a wave of higher intensity. If the peak of one wave overlaps with the trough of another wave, however, the result is a wave of lower intensity. By applying this logic, Young was able to predict the pattern of bright and dark bands that he observed on the screen. This experiment is now known as Young's double-slit experiment. It's a classic demonstration of wave-particle duality, which is the idea that light and matter exhibit both wave-like and particle-like properties. Young himself didn't really consider the implications of his experiment. He was primarily interested in understanding how the eye sees color. It wasn't until nearly 200 years later that physicists began seriously considering the implications of his double-slit experiment. One of these physicists was Richard Feynman, who would later win a Nobel Prize for his work on quantum electrodynamics. Feynman was fascinated by Young's double-slit experiment because it illustrated the fundamental difference between classical mechanics and quantum mechanics. According to classical mechanics, if you were to fire a single particle at the double slit, it would pass through one slit or the other, creating two separate points of light on the screen. According to quantum mechanics, however, the particle would pass through both slits, creating an interference pattern of alternating bright and dark bands. Feynman was so enamored with this experiment that he devoted an entire chapter of his lectures on quantum mechanics to it. He said that the double-slit experiment is the heart of quantum mechanics, in which the classical ideas that were previously used to describe nature ultimately failed. There is an experiment that shouldn't exist. It was first done in 1801 by British polymath Thomas Young, who basically invented the modern scientific method. He's also the reason we have the metric system. It's him. But this experiment he did in 1801 has been called the most important experiment in the history of science. It's definitely one of my favorites, and it's called the double-slit experiment. Now there are lots of versions of the double-slit experiment. This is the earliest version, and it doesn't involve any quantum mechanics or particles at all. And I think it's the best one. Let me show you why. We'll start with some backstory. So Thomas Young was a really smart dude. I mean, really smart. like he could see colors when he was 2 years old. By age 14, he had invented his own version of calculus, and by age 24, he had published over 70 papers in mathematics, physics, and chemistry. Also, he was a linguist, and he learned ancient Greek, and then used that to help decipher Egyptian hieroglyphics. And he also invented the all-at-once method for measuring longitude and the reflecting telescope. Yeah, and he's not even the most interesting part of this story. The year before Young performed his famous experiment, William Hyde Wollaston noticed something while looking through a thin film of glass. He saw bright lines in the spectrum of light. These became known as the dark fringes in Young's double-slit experiment. But Young didn't discover them. Instead, he discovered interference. To tell the story, I need to introduce you to a character, the wave. Waves have peaks and troughs. When two waves overlap, the peaks and troughs can either add up to make bigger waves or cancel each other out, depending on whether they're in phase. This is called interference. In 1801, Thomas Young set out to explain what he observed. He wanted to know if light waves interfered like water waves. If they did, the next question was, why? Why do they interfere? To answer these questions, he designed an experiment. Here's how it went. First, he picked a source of light, a candle. Then he created a barrier with 2 narrow slits cut into it. Next, he put a screen behind the barrier and moved it until he saw an interference pattern. He got what we call an Airy function. What does it mean? It means light waves from different parts of the candle combined constructively, destructively, forming alternating bands of bright and dark fringes. And now comes the weird part. Young changed the color of the light source. At first, the pattern disappeared, but then he switched back to white light and voila, the pattern reappeared. The interference pattern was created by a combination of all the colors of light. He then switched things up. He used a blue and red filter, so only one color of light could pass through the slits at a time. In this case, only blue. Again, no interference. But then he replaced the filters with a prism, and suddenly there was interference. Each color made its own fringes. And here's where the results get weird. Young separated the colors enough that each had its own fringe, and then he removed the prism, but he kept the blue and red filters, so only blue light could pass through the slits. He thought that since the blue light was now separated into its own fringes, there wouldn't be any interference. But then he started moving the filters apart, and the fringe pattern slowly returned. The separated colors began to blend together, and the entire pattern started to glow again. And this is the weirdest part. It was almost like the colors knew where the other colors were. It was as if the colors were communicating. How could that be? How could the colors know about each other? Well, let me bring in another character, Mr. Particle. You see, particles don't interfere like waves do. They just go straight through the slits. If Young's experiment was only about particles, you would expect to see 2 bright bands where the particles passed through the slits. But obviously, that wasn't what happened. So to explain his observations, Young proposed that light was made of waves, specifically what we today call electromagnetic radiation. But this idea wasn't new. Lots of people had proposed it before Young. Newton himself believed light was a wave, which is why he developed corpuscular theory. Basically, he said light was made of particles, but those particles behaved like waves. The problem with Newton's idea is that it couldn't explain things like diffraction. It couldn't explain why light bends around corners. So generally, scientists rejected the idea that light was made of particles. What made Young's experiment so important is that it gave strong evidence for the wave theory of light, but it did it without relying on any other observations. It wasn't based on any mathematical models. Young didn't try to calculate anything. He simply described what he saw. His results were qualitative, not quantitative. Because of this, Young's experiment helped establish the wave theory of light, which eventually led to Maxwell's equations and Einstein's theories of special and general relativity. You know, those theories that I talk about all the time on this channel. If that's not enough, Young's experiment also played a role in quantum mechanics, because in 1927, Clinton Davison and Lester Germer repeated Young's experiment with electrons. Remember how Young showed that light from different colors interferes? Well, Davison and Germer showed that electrons from different energies did the same thing. That result led to the development of quantum mechanics. But again, I want to emphasize that this isn't the quantum double-slit experiment. There aren't any quantum effects. All I'm saying is that this experiment was the inspiration for later experiments that later inspired quantum mechanics. In science, we often get lost in the math and the models and forget about the real world. We lose sight of the trees and miss the forest. And Young's experiment is a great reminder about how we use simple observations to build up our understanding of the universe. It's about reducing complexity and finding patterns. It's the exact opposite of how most science videos work. Like in a science video, we usually start with a really simple observation, like a rainbow. Then we build up this elaborate model with concepts like wavelengths and frequencies and superpositions and entanglement. And that's kind of neat. But every now and then we should step back and remember that science isn't just about complex ideas. It's also about appreciating the beauty of the world around us. Now let's move on to Newton versus Huygens, the light wars. What if light is made of tiny little balls? It might make you think of a child's marble run, or maybe a particularly violent game of dodgeball. But for Isaac Newton, it was the key to understanding how light works. In fact, he thought this so hard that he decided the whole universe must be made of tiny balls. Not just light, everything must be made of them. Everything we see around us is composed of corpuscles, little solid objects that are in constant motion. Everything in the universe is either at rest or moving in a straight line with constant speed until another corpuscle smashes into it. In other words, Newton thought the universe ran on billiard ball physics. This model was not completely useless. It could explain some things that were known about light and mechanics. But in reality, this model didn't make any sense, because there were things that the corpuscle couldn't explain, like diffraction, which is when waves spread through small openings. Also, it didn't really explain why light behaved like a wave sometimes and a particle sometimes. And also, it didn't explain why light traveled at different speeds depending on what medium it was passing through, like air versus water. But the thing is, Newton was wrong, but he wasn't alone. He had a whole team of people that believed this same thing as him. The corpuscle theory had its roots in the work of the great Galileo Galilei, who had proposed that light was made of particles called minute bodies, though he never took his idea further than that. Newton himself built on the work of both Christian Huygens and Robert Hooke. Both of them had ideas that weren't too dissimilar from Newton's own, though they differed in important details. Both were in agreement that light was made up of particles, but they disagreed on what exactly those particles did and how they interacted with each other. So given that most scientists at the time thought light was made of corpuscles, why am I telling you that Newton was wrong? Well, because he lost the light wars. It's true that Newton's corpuscle theory was popular in England, but on the continent, it was a different story. There, Christian Huygens' wave theory of light was all the rage. Huygens was a Dutch physicist and mathematician whose work was foundational to our understanding of optics. In 1678, he published a book called De La, which contained his wave theory of light. This theory proposed that light was a wave phenomenon and that it propagated through a hypothetical medium called luminiferous ether. The reason I say hypothetical is because later it turned out that light didn't need such a medium and it could travel through a vacuum. But at the time, this was the best explanation we had for how light worked. Light travels in a wave-like manner, Huygens argued, because every point on a wavefront acts as a source of secondary spherical wavelets. These secondary wavelets spread out in all directions and they interfere with each other, creating a new wavefront. This is now called Huygens' principle. It's a useful tool for determining how light behaves when it interacts with different objects. It's like when you drop a pebble into a pond and then the ripples spread outwards. Now, instead of ripples, we're talking about light. And instead of the surface of a pond, we're talking about points in space. Each of those points acts as a source of a wave that spreads outward in all directions. These secondary waves then add together to form the next wave front. This can explain how light bends around corners, for example. Now, of course, the wave theory of light had its own problems. First of all, physicists didn't know what the luminiferous ether was, and that kind of remained unexplained. Second, it couldn't explain polarization. Polarization is a property of transverse waves. It refers to the orientation of the oscillations relative to the direction of wave propagation. A simple way to think about it is that if the wave is vibrating up and down, that's one polarization. But if it's vibrating side to side, that's another polarization. You can even have a wave that's vibrating in more than one polarization at once. Third, the wave theory couldn't explain the photoelectric effect, which is when electrons are emitted from a metal plate when light shines on it. This is a quantum effect. Light doesn't act like a wave here. Instead, it behaves like a stream of particles called photons. We know now that light is both a particle and a wave. This is called wave-particle duality. Sometimes it behaves like a particle, like in the photoelectric effect, and sometimes it behaves like a wave, like when we see an interference pattern. However, the thing is, these three problems were not well understood at the time, and therefore, the wave theory still did a better job explaining light than the corpuscle theory. Now, while it's true that the wave theory of light had its own problems, they were nothing compared to the problems of the corpuscle theory. That's because the corpuscle theory didn't explain basic phenomena that everyone had observed, such as refraction and interference. Newton tried to explain these away by claiming that these phenomena happened in a special medium called the ether, but he never identified what medium he was talking about. So it was basically an invisible ether, and that doesn't really count. Now, not only did Newton's corpuscle theory not explain observed phenomena, it also made predictions that were clearly wrong, like that light would travel at the same speed through empty space and through matter. Again, Newton tried to explain this away by inventing yet another hypothetical substance called the luminiferous ether, but that doesn't really count because, again, it was invisible. And not only that, but he also claimed that the Earth was at the center of this luminiferous ether, which made no sense because if that was true, then stars should rotate around the Earth, which obviously they don't. The final nail in the coffin for Newton's corpuscle theory came when James Clerk Maxwell developed his equations, which predicted that electromagnetic waves traveled at the speed of light. This meant that light was an electromagnetic wave, and thus it must behave according to the laws of wave mechanics. Newton died in 1727, so he never saw this development. However, his friend and colleague, Edmund Custis, did. Custis was a strong proponent of the corpuscle theory, but even he eventually admitted defeat. There's a letter he wrote to a friend which goes, "As to Mr. Newton's optics, they are, in my opinion, erroneous and will in time be entirely exploded. The notion of colors arising from the different refrangibility of light is absolutely false." While most scientists accepted the wave theory of light, Newton's ideas didn't go to waste. His ideas about corpuscles inspired the development of kinetic theory, which describes how the properties of matter are related to the motion of its constituent particles. This led to the development of statistical mechanics and eventually to the laws of thermodynamics. And, ironically, it was Newton's work on corpuscles that laid the foundation for the development of quantum mechanics, which ultimately led to our current understanding of wave-particle duality. In the spring of 1666, Christian Huygens was about to pull off one of the greatest upsets in physics history. He was going to prove that light is a wave, a discovery that would cast doubt on his rival Isaac Newton's corpuscular theory of light. But first, he needed an observation from the other side of the world. Isaac Newton had published the first of his 3 laws of motion in 1687, and the calculus he co-developed with Gottfried Wilhelm Leibniz was all the rage. But Huygens, who had been in London since 1660, had his own accomplishments to brag about. He built an improved version of the pendulum clock, discovered the ring structure of Saturn's largest moon, Titan, and proposed a new theory of color vision. Plus, he was building a reputation as something of a statesman in science. It was he who convinced the king to establish the Royal Society in 1662, and he served as its president from 1679 to 1682. He was also the first foreign scientist admitted to the French Academy of Sciences, but it was their ideas about light that set Newton and Huygens on a collision course. And that brings us to the spring of 1666. Huygens wanted to demonstrate that light behaves like a wave, and there was a lot of observational evidence to support his claim. For instance, when light passes through a narrow slit, it spreads out after passing through, which couldn't happen if light were made up of particles. So all he needed to complete his proof was a way to measure the wavelength of light, and he thought someone could help him out. You see, light from distant stars and planets reflects light from the sun. And if he could just measure the wavelength of a star's light when it passed through a prism, then he could determine the wavelength of sunlight by dividing the two. Unfortunately, measuring the wavelength of starlight was beyond the technology of the time. It was not until 1881 that the Italian physicist Angelo Secchi accurately measured the wavelength of light from a star. But Huygens had a backup plan. Huygens had corresponded with Edmund Custis, an English natural philosopher who had a particularly keen eye for detail. Custis had done some experiments where he mixed ground glass with water and then shone a light through the suspension. He observed that the colors in the resulting spectrum were different depending on the size of the particles. He suspected that this was because the particles were diffracting the light, and if so, then maybe he could use the diffraction pattern produced by those particles to measure the wavelength of light. In principle, this would work because the spacing between maxima in the diffraction pattern is given by d times sin equals m times lambda, where d is the distance between the diffracting particles, theta is the angle from the central maximum, m is the order of the maximum, and lambda is the wavelength of light. If he knew the value of d, the angle, theta, and m, then he could calculate lambda. But in practice, it didn't quite work out that way. The problem is that in Costa's experiments, the light was only passing through a few particles at most before hitting the screen, and without knowing the exact distance between each pair of particles, there were too many variables to solve for lambda. But that didn't stop Huygens from asking Costas for more data. Specifically, he requested that Costas prepare a sample of particles that have uniform sizes and distances between them. And that meant grinding a very large number of tiny pieces of glass into uniform disks. Even by modern standards, that would be a tedious task, but for 17th century England, it was borderline impossible. But Quist was determined to make this work because, well, England was in the middle of a civil war. No, really. There was a period of relative calm between 1666 and 1668, known as the 2-year truce. But fighting continued intermittently, and in June of 1666, the Scottish army invaded England. So, as bombs fell around him, Costas got to work. He ground down thousands of disks of glass, until finally he had a sample that yielded a diffraction pattern with bright fringes spread across the entire spectrum. Then he went to see Huygens with the results. But it was too late. A few months earlier, Newton had submitted his own paper on the diffraction of light to the Royal Society, and in it he offered a different explanation for what was going on. In Newton's mind, light was made up of particles called corpuscles that were emitted from a source in all directions. They moved with a constant velocity, traveled in straight lines, and possessed a momentum that depended on the frequency of the light. When light hits an obstacle or aperture, the particles are deflected in accordance with the laws of motion. And Newton used this corpuscular theory to explain both the central maximum and the minima in the diffraction pattern. And Newton wasn't just some armchair theorist. He built his own device to test his hypothesis and showed that the intensity of the diffraction pattern he produced matched what he predicted. At first, Huygens was skeptical of Newton's explanation. After all, he himself had already shown that light bends around obstacles, which seemed to require a wave-like medium. But then he did something unexpected. He took a closer look at Coote's data and realized that Newton's explanation actually fit it better. It turned out that Quesada's samples weren't as uniform as he thought they were, and Newton's explanation accounted for the deviations in the data better than Huygens did. Huygens' particle theory of light had dealt a death blow to Descartes' wave theory a few decades earlier, and now it was happening to him. To make matters worse, Newton's explanation left no room for Huygens' theory of colors. Newton believed that white light was made up of an infinite number of differently colored corpuscles, which contradicted Huygens' explanation, which stated that color is determined by the peaks and valleys of light waves interfering with one another. So what was a poor guy to do? Well, he decided to appeal to authority, specifically Robert Hooke, a polymath whose contributions to science included the discovery of cells, the explanation of elasticity, and the invention of the decimal point. Hooke had been critical of both Newton and Huygens in the past, but now he sided with Newton. So in the end, Newton won the argument. But that doesn't mean he was right. In fact, we now know that light is a wave. In the early 1900s, Albert Einstein explained the photoelectric effect by proposing that light comes in discrete packets of energy known as photons. Those photons behave like waves, but they also exhibit particle-like properties. So light is both a wave and a particle. It's just not either or. And if Newton had lived to see quantum mechanics, he might have embraced this duality. But he died in 1727, long before the dawn of quantum mechanics. And the great irony is that Newton's victory over Huygens was based on a misunderstanding of exactly how quantum mechanics works. A lot has been written about the feud between Newton and Huygens, but one thing that often gets overlooked is that the two men never actually met. You see, Newton spent almost his entire career at Trinity College, Cambridge, whereas Huygens lived and worked in Paris. By the time Huygens visited England in 1667, Newton had taken a leave of absence from Trinity to take care of his father's estate. And by the time Newton returned to Cambridge, Huygens was back in Paris. They had exchanged letters, but never met face to face. Yet their rivalry defined their careers and helped shape the course of physics. Now you're probably wondering what happened to Costas. Well, following the Restoration, he was knighted and became the Master of the Mint. He died in 1703. As for Newton and Huygens, they each went on to publish more groundbreaking work, but unfortunately, their relationship never improved. Now let's dive into what we knew about light before electricity. Before there was electricity, there was candlelight. We take candles for granted these days, but they're actually pretty miraculous. They're like tiny little controlled explosions that burn steadily and reliably and can last for hours. And one of the things we learned from them is how light works. Join me today as we find out what we knew about light before electricity. It's easy to take something we've always had for granted, like light from an electrical outlet. But it wasn't too long ago that electric light was a new invention. And before that, candles were the way people lit their homes at night. They might not have been the first way, but they were by far the most common. So if you wanted to make a candle, you needed 3 basic ingredients: a candle wick, some sort of fuel, and a container. The earliest practical candles were made by dipping a wick into hot animal fat over and over until it was coated with enough wax to burn properly. This isn't the best method, but it works. And you probably don't want to improve it much, because hot wax is extremely flammable and will burn your house down if you aren't careful. But to understand why that happens, let's talk a little bit about the science of candles. A candle consists of a fuel source, usually in the form of wax, and a wick, which is typically made of braided string. When the candle is lit, the heat from the flame melts the wax. That liquid wax is drawn up through the wick by capillary action, just like water climbing up a straw. And as it reaches the top of the wick, it vaporizes. That hot wax vapor mixes with oxygen from the air and combusts, creating a flame. The heat from the flame then melts more wax, and the cycle continues until all the wax is used up or the candle is otherwise extinguished. This means a candle has 2 parts to its flame. There's the visible part, the part that gives off light and heat, and then there's an invisible part where the wax is actually turning into a gas. Because of this, a candle flame isn't actually hot. In fact, the hottest part of a candle flame is the invisible part. The visible part is what we're interested in when we're talking about light, though. and it's also the part that has fascinated humans the longest. People have known about candles for around 3,000 years. Ever since ancient Egyptians discovered that they could melt animal fats and pour them onto papyrus reeds, which would then burn and give off light. But it wasn't until the early 17th century that people started experimenting with candles in a more scientific manner. One of the people who did this was a Danish scientist named Rasmus Bartholinus. He was interested in studying how light worked, and he decided to use candles for his experiments. He noticed that if he put a shutter over his candle flame, it went out. And he used this observation to come up with one of the earliest theories of light. He believed that light needed something called an ether in order to travel. Ether is a hypothetical substance that was proposed in the mid-19th century to carry electromagnetic waves. Basically, it's like space goo that fills the universe and allows light to travel through it. While we now know that light doesn't need any special substance to travel, this was the best theory scientists had at the time. Bartholomew's experiment with the shutter led him to believe that light traveled in straight lines, and he was even able to measure the speed of light by timing how long it took for a beam of light to travel between 2 points. He also noticed that if he placed an object in front of a candle flame, it cast a shadow. And he used this observation to come up with another theory of light. He believed that light was made up of tiny particles that were emitted from the candle flame. These particles traveled in straight lines until they hit an object, at which point they bounced off, just like light would if it were made up of particles. Now, while Bartholomew's theory of light particles was incorrect, he was on the right track. Today, we know that light is made up of waves of electromagnetic energy, and these waves can travel through a vacuum, like space, without needing any special substance, like ether. And while they do travel in a straight line, they don't bounce off objects like billiard balls. Instead, they bend around edges, spread out after passing through small openings, and otherwise act like waves. But before Einstein came along and told us all about this, people were still trying to figure out what light was made of. One of the ways they did this was by looking at shadows. Shadows are an everyday occurrence. Every time an object blocks light, one gets cast behind it. But before modern technology, shadows weren't always easy to see. Usually they were subtle and often blended into the. In 1617, a German astronomer named Johannes Kepler published a book called Dioptrics, in which he discussed how shadows work. He used a candle flame and a small piece of paper to demonstrate that shadows were really just the absence of light. He also noted that shadows were always the same shape as the object that cast them, just reversed. And he used this observation to come up with his own theory of light. He believed that light was made up of tiny particles that were emitted from the candle flame in all directions. If the particles ran into an object, they would bounce off in a different direction, and if they hit a surface, they would be absorbed and re-emitted, creating a shadow. Again, this wasn't correct, but it was close. What he was actually observing was the interaction between light waves and matter. Light waves travel through space at a constant speed, and when they hit an object, they do one of three things. They get absorbed by the object and converted into other forms of energy. They get reflected by the object and continue traveling in a different direction, or they pass through the object and continue traveling in a straight line. So if we have a candle flame and an opaque object, some of the light waves will be absorbed by the object and converted into heat energy, while others will be reflected and bounce back into our eyes. That's what we see as the shadow of the object. So while Kepler's idea that light was made up of particles was incorrect, his observations of shadows were actually quite accurate. His ideas were later expanded upon by his student, a German mathematician and astronomer named Johann von Lamy, who built on Kepler's work to develop a more complete theory of light. Like Kepler, von Lamy believed that light was made up of particles that were emitted from a source in straight lines. But he also believed that these particles could be polarized. Polarization is a property of waves that describes the orientation of the wave relative to the direction of motion. For example, if I were to take a rope and flick it up and down, I would be creating a transverse wave. Now if I were to instead flick the rope side to side, I would be creating a different type of wave. This is called a longitudinal wave. Light waves are transverse waves, and Vlam believed that if you looked at a shadow cast by an object, the polarization of the light waves would change depending on the angle of incidence. This would mean that shadows wouldn't just be dark areas, they would also be colored differently, depending on the angle of incidence. He also believed that if you took a long, thin piece of material and placed it in front of a candle flame, it would cast a rainbow-like shadow behind it. And in 1664, he proved this by doing just that with a thin plate of tourmaline. This experiment led von Lamy to conclude that light was made up of many different types of particles, each of which vibrated in a different plane. While von Lamy's ideas were closer to the truth than anyone else's before him, he was still wrong. Today, we know that light is made up of waves of electromagnetic energy that vibrate in all planes, and those waves can be split up into different colors by a prism, not because they're different types of particles, but because they interact with matter in different ways. But regardless of whether or not they had the correct understanding of light, people still used their knowledge of shadows to their advantage. As early as the 16th century, scientists were using candles and shadows to tell time. They would place a candle at one end of a room and then mark the position of its shadow on the wall. Then they would repeat this process at regular intervals, and by measuring the distance between the shadows, they could tell the time that had passed. This is essentially the same way a sundial works, except instead of using the sun, they were using a candle. Candles were also used to create moving shadows, which led to the invention of shadow puppets. Shadow puppets are a form of storytelling that uses silhouettes to represent people, animals, or objects. They were likely invented in China as early as the 2nd century AD, and they quickly spread to other parts of the world. In Europe, they became popular during the Middle Ages, when traveling entertainers would use them to tell stories in taverns and at festivals. These days, we often think of light as something that just happens. We flip a switch and light appears. But that wasn't always the case. For most of human history, light had to be produced, whether by harnessing the power of the sun or burning a controlled mixture of chemicals. Even with the advent of electricity, light still had to be generated by a power plant somewhere. And it wasn't until recently that we started thinking about how to send light signals through fiber optic cables. Today, light is so ubiquitous that we often take it for granted. But it's only relatively recently that we figured out how it works. Most people think that electricity came about because we wanted light bulbs. And it's true that Thomas Edison and his contemporaries were looking for ways to harness electricity in order to produce light. But also that we needed light in order to have an electric system that could be widely used by lots of different people. But what did people think light was made of before electricity? The answer is surprisingly complex. In the late 18th century, there were three main hypotheses on how light traveled from one place to another. One was that it was carried by particles called corpuscles, which we now know isn't really true. Another was that it was carried by waves, like water waves, which is partially true. And the third hypothesis was that light was carried by a mysterious substance called the luminiferous ether, which turned out not to be true at all. Let's start with what was known. Since antiquity, humans had observed the behavior of light when bouncing it off different materials. Sometimes light would bounce right back in the same direction, like when sunlight bounces off a mirror. But other times, light would bounce in a different direction, or not at all. People started to notice regularities in this behavior. They noticed that some materials seemed to redirect light in predictable ways, and they could even calculate what those predictable ways were. In fact, these calculations worked so well that mathematicians started to say things like, if you shoot light down onto a pane of glass at a certain angle, then the light that gets bounced back will always come out at exactly such and such an angle. This idea of predictability was extremely important for how people thought about light. It implied that light behaved according to rules, that it acted like a machine, which led people to think that maybe it was made of particles. This idea was first proposed by the Greek philosopher Euclid around 300 BC, and then again later by the Roman philosopher Lucretius around 100 BC. They imagined that just like balls could collide with each other, light could be made of little corpuscles that collided with each other. There was just one problem, and that was that sometimes light passed through stuff without changing direction at all. And if light was made of little hard balls, you would expect that to change its direction all the time. So as far as this theory could go, it didn't really explain how light worked. It only explained some of the things that light did. Around the year 1600, the English physicist Robert Hooke thought he might have solved this problem. He looked at light through a prism and noticed that it bent when passing through. That meant that light must be made of something that had weight and mass. Otherwise, it couldn't bend under the force of gravity. This particle theory, therefore, had the advantage of explaining why sometimes light went straight through objects and other times it changed direction. If light was made of particles, then the spaces between those particles would let light pass through easily, but bumping into one of the particles would change its course. Unfortunately, there was a slight problem with this theory, and that was that it didn't actually explain anything. You see, Hooke had no idea what these particles were made of. All he knew was that they had mass, and this was a big stumbling block for physicists throughout the 17th and 18th centuries. You see, if light was made of particles, where did those particles come from? And if they were made of something else, then what was that made of? And if that was made of something else, then what was that made of? In short, light couldn't be made of anything, and so physicists abandoned the idea, at least for a while. But the question of what light was made of wasn't purely abstract. After all, Hooke was trying to figure out how telescopes worked, and if you want to make a good telescope, you need to know how light works. To his credit, Hooke was able to use his particle theory of light to make some pretty good guesses about how telescopes worked, and he ended up inventing the first compound microscope. By the end of the 18th century, however, most scientists had come to agree that light was made of waves, much like water waves crashing on the beach. Water waves move up and down as they travel, and if you drop a pebble into the water, the waves spread out in circles from that point. Light waves would work the same way, except that you wouldn't see them moving up and down. Instead, they'd be wiggling from side to side. Moreover, when light hit an object, it would wiggle the electrons inside that object, just like water waves bobbing up and down wiggle the water molecules inside a glass. And when those electrons wiggled, they would re-emit light waves, which is why some objects, like mirrors, reflect light. There was just one problem, and that was that light waves couldn't travel through a vacuum. Like if you remove all the water from the ocean, you can't have waves on it. And scientists knew that light could travel through empty space. So the wave theory of light, just like the particle theory of light, couldn't explain everything that light did. And so, in 1849, a physicist named Augustin Fresnel came up with the idea that light was carried by a mysterious substance that he called the luminiferous ether. The ether would act just like the surface of the ocean, carrying the light waves across the vacuum of space. Waves could travel through the ether, and the ether would just jiggle along with them. Now physicists finally had a complete explanation of how light worked, or so they thought. The trouble was that nobody knew what the ether was made of. The best guess was that it was made of particles, but physicists knew that couldn't be right, because if it was, then it would bump into atoms in the way of a beam of light and change its direction. They also knew that the particles couldn't be bigger than atoms, otherwise the light would just rip straight through them. And they also knew that the particles couldn't be smaller than atoms, otherwise they wouldn't be able to carry the light waves. So light couldn't be made of particles. It couldn't be made of anything. And as it turned out, it wasn't made of anything because light isn't made of anything. Light is just the jiggling of empty space. It doesn't need anything to carry it. None of the scientists who thought that light was made of anything actually got it wrong. It's not that they didn't understand the nature of light. It's that they didn't know what they were missing. You see, they knew that light behaved like a wave, but they also knew that it behaved like a particle. It wasn't until the 20th century that scientists realized that light was both a wave and a particle at the same time. Now, you might think that scientists were slow to figure this out, and you're right. But you might also be surprised to learn that scientists still don't know what exactly light is. Scientists today are aware that light is both a wave and a particle, but they don't really know what either of those things means. Like, if you ask what a wave is, most physicists will say it's a transfer of energy through a medium. But if you ask what a particle is, most physicists will say it's a localized region of non-zero probability for finding a wave. Basically, scientists don't really know what light is, and it seems like they never have. Now, there's nothing particularly interesting about not knowing what light is. Lots of things don't act like particles, and don't act like waves, like heat, or magnetism, or sound. These things act like themselves, and it took us a long time to figure out what those things were. But unlike heat and magnetism and sound, light is extremely useful. It has all sorts of practical applications. And that means that even though scientists don't know what light is, they've still been able to use it to do amazing things. Light is what allows us to see the world around us, and it's also what allows us to communicate with each other across great distances. With light, we can send information around the entire globe in less than a second. Light is what makes photography and telecommunications and fiber optics possible. In short, light is what makes modern life possible. It's strange to think that the world would be so different without light. But it's also strange to think that we still don't know what light is. So if you're ever sitting around wondering why your Wi-Fi is so slow, or why your phone battery dies so quickly, just remember that at least you get to see the beautiful blue sky. You don't need to understand light to be comforted by it. Sometimes, what we don't see clearly is still enough to guide us.